Okay, so you are meant as an engineer, if you are a consultant, you can come from the angle of being a consultant or from the angle of being an engineer who is supervising a road, a water project, water distribution project, water reticulation project, water infrastructure project. So the first thing you need is a map of the area. And that map will not just be an area map, it must be a map that have information. And those information must be topographical information or elevation information, what we call spot heights. And or you could say it must have contours. Why is this necessary? Because remember, 90% of water reticulation system is by gravity. So it means you don't require pump except to take water from source to the overhead tank. So to this, and what we are doing, our focus is from the overhead tank or reservoir to the consumers. That's our focus. So it means that you are playing around with natural terrain. You are playing around with, you have an existing pressure and you have to manage it and get the best out of it. So when you are giving information like this, a map, the next thing you should require is to get the elevation information, or you send your surveyor to go and take levels. You need that levels because the first thing you need to do is to determine where to site your overhead storage tank, since you're going to supply the water via gravity. So your point would be, where is the most convenient place vis-a-vis safe and elevated? So for you to have this information, it means that the surveyor must go to site and determine those parameters. So this is a case study of what we're going to look into. As you can see, those black dots represent buildings and the lines represent the elevations, or as we usually call them, the contour lines. Now, when you finish your network, this is what your network is going to be like. You're going to follow the path of the right of way, the path of the road, because you're not going to follow your pipeline through people's property. So you're going to follow, if you look at this drawing and you look at this one, you know that they are quite similar. Then the next thing you do is you now go to your Excel and develop a table that looks like this. It's a standard table. You can customize it. You can bring up a variant of this, but this is information that you are required. And I think I mentioned it yesterday that for you to do a water reticulation system, you need about 4 parameters. 4 parameters is what you need. So those tables must show those 4 parameters. And those parameters that you need are for the pipe, 2 are in the pipe. Hope you can see my screen. So you need 2 pipe parameters. Just hold on. Okay. So you need 2 pipe parameters. And for the pipe, what are those 2 parameters you need for the pipe? They are the elevation. No, sorry, the length of the pipe and the diameter of the pipe. So your table must show the length of each pipe or each section, and it must show the diameter of those pipes. Even while you're detailing your work, you should also follow the same convention. Then the next you need is what I call node parameters. You need pipe parameters and node parameters. Pipe parameters and node parameters. So the 2 pipe parameters are your length. Every pipe must have a length. Every pipe must have a diameter. Then for the nodes, every node must have an elevation. You must know the elevation at every node. And then you must know the demand, the water demand. Let me just say demand, it means the water demand. What are we demanding for? Is water that we are doing. So you must have a demand at every session. This demand can also be called the flow, which of course we know is Q. So at every node, you should know the the demand at that node, because many houses might be connected to that node. So you must know the demand at every node. And at the same time, you are supposed to know the elevation at that node so that you can know the corresponding pressure at that point. Then for the pipes, you need the length, you need to know the length for you to be able to calculate the frictional losses. And then you need to know the diameter for you to be able to know if the diameter is enough to convey that flow. So that's exactly what we have here. So, but to determine those 4 parameters, you might need other parameters. For instance, you must have a beginning and an end. So this is storage tank to point 1, point 1 to point 2, point 3 to point 4, point 4 to point 3. So if you are looking at this, you relate it with this. So this is storage tank position to node 1, node 1 to node 2, node 1 to node 4, because here node 1 has 2 branches. It has branch 1, it has branch 2. If you come to node 4 have about 3 other branches. It has 3, it has 5, and it has 8. Okay, so it means he's distributing water to people who are along this corridor, people along this corridor, people along this corridor, and so on and so forth. Okay. So what we have here is just a translation of the layout details. The layout details, you put it into a template or a format like this. So your job, our job today, is to fill this table. If you're able to fill this table, then your job is done. The next thing you do is you take it to the computer Epanet, where you now model it. And I always say this in some of my classes. There's no computer software that does design. What computer software do is to model and simulate. It is you, the engineer, that will do your design. It is after you have done your design that you now create a model. You now use a computer to create a model so that if adventure tomorrow something changes, you don't have to start from scratch again. It means you simply have to come to your model and then change the parameters of that model. Sometimes you have to move the boundary condition. Okay. So you have to move the boundary condition and still achieve your design. So here now you can see that for me to achieve the length of these pipes, I need to know the starting point and the end point. So like from the storage tank to elevation 1, the length is 120 meters. From point 1 to point 2 is 60 meters. From point 1 to, so I can measure it with AutoCAD. If the drawing was given to me in an AutoCAD format, I can easily measure it and then get the length. Remember again, what we are looking for us to be able to design our network are 4 parameters, just 4. We need 4 input parameters, and that's exactly what the consultant, the engineer, the contractor, the executor want from you. He wants to know the length of each pipe so that he can be able to cost it. He wants to understand the diameter of each pipe so that he knows which one to buy in the market. Then he wants to know the elevation, because the elevation will also help him to know how far he has to dig to be able to achieve that slope. And then he has to know the demand, because you, the engineer, the demand is what will help you determine the diameter of the pipe. Without the flow, without knowing the required demand, you cannot determine the pipe. Yesterday, I told us that for you to design any pipe network, whether gas, oil, sewer, sewage, you need to know the flow. What flow am I trying to conduct safely? If the flow is much, the diameter will be much. If the flow is small, the diameter will be small. So if you make a mistake, the water will not flow, or there won't be adequate water for the end consumers. And that is why it's important that you understand how to achieve both. So those 4 parameters, 1 has been achieved. So if surveyor gives you his data or it has been plotted on a layout, it's easy for you to know the diameter, the distances, because you can easily use your mouse, use your inquiry tools on AutoCAD, and you mark them out. That is so simple. After that, what do? The surveyor can also give you the elevation, because when you send the surveyor to site, part of his job is to get you the SY coordinates, which you use for your road design, which the surveyor will use for the road aspect. Then you, the infrastructure engineer, the water engineer, will now use the spot height, the elevation, to now do your own design. That's why in most infrastructure work, it is the road designer that goes in first. Oh, sorry, the surveyor goes in first. And when the surveyor gets his data, he creates one and plot it for the road designer, and then plot it for the infrastructure designer. The infrastructure designer, what he needs from the surveyor are the road, are the length, which he himself can call out, and the elevation, which can only be done by either a total station, or which can only be done by a survey instrument. Let me not go into details. So automatically from the survey data, we already have two information. And if you look at this drawing also, you can agree with me that every engineer can extract these two information here. It's very easy to extract these two information here. Okay, you can extract these two information from this layout, which is the length of each section, and then the elevation at every point. So let me bring up us again to what we did yesterday. So after this elevation and everything, we now have to go and find out how we can get our Q. So if you look at the next item on this table, hold on. If you look at the item on this table, just stay with me. Okay. So the next item says the Q. Okay. So we have the Q. We don't know the Q now. So the first thing you now do is to determine the Q. And that was why in our lecture yesterday by my colleague, he told us that after you have done your mapping, the next thing is you do your water demand determination. You do your population projection to get the exact number to use. And I say it again, if you are designing for 50-year lifespan, it is the population after 50 years that you use. That is why you need to project your population to the future, to also project your rate of development to the future. And that is why the issue of land use is very, very important. Yeah, Engineer John, Aboifo, there's a question on your direct this thing. Okay, somebody say, how can we be put through on how your table was generated? Okay, that's a good question, and that's exactly what I'm saying. Maybe you have already seen it. This is a table. If you go online, you can download any templates. It's just this Excel. So from what the surveyor gave you, this is what surveyor gave me. Okay, so I need to bring it into a table. So if you look at it, you see that storage tank is at elevation 310. This is node 1. Node 1 is passing through 28. This is 280, and this is 270. So number 1 is around elevation 280. But a good surveyor will give you this information in Excel. If you're an infrastructure person, you know that surveyor will give you the result in Excel formats. The points, X, Y, X coordinates, Y coordinates, elevation, and maybe the description. Or the longitude, the latitude, the elevation, the description, whatever format he uses. So this can come from the surveyor. But if you have a layout like this, you can also read it out. So you can see this point is 280 something. So if you go to my drawing now, you see that it is at 279. 279 and 280 are almost the same thing. Okay. Look at this point now, this last point here. This is point 13. This is point 13. Okay. So if you go to the layout, you will see that point 13 is at 210. Point 13 is at 210. So if you come here and look very well from the contour line, this is no, I'm wrong, sorry, not 210. That 210 is the distance. Point 13 is 252. That's elevation. So if you come down here, you can see that here this is 252 because this is 250, this is 260. So somewhere this point where my cursor is, which is point 13, is 252. Are you okay with that, sir? I hope so.
Yes, I am.
Okay. Engineer John Paul. Okay. Thank you.
No, it's Engineer Richard Antega.
Okay. Okay. Thank you. Okay. So that is that. Okay, somebody say, what is a node? Well, a node is more like a manhole. A node, thank you, that's a good question too. A node is, I want you to imagine a node as a manhole, okay, where two pipes will meet. So your node can also be assumed to be, if your surveyor is taking his level every 20 meters, it means you can establish a node after 20 meters. If he's taking his level after every 50 meters, you can assume it's a node. It's just a reference point where the elevation details are known. What it does is that it helps you to calculate your slope. Remember slope. Slope is the difference in height over difference in over length. Sorry, difference in height over longitudinal distance. Sorry, let me just project my whiteboard a little bit. Okay, we all remember how we compute our slope. Our slope is something like this. Okay.
H1 minus H2 over L.
Thank you. So if I have a surveyor walking from here, okay, he comes here, this place is say 0. So this is where he started. And he's going to walk and be taking spot height. And here is say 20. Okay. And thank you. And here says, let's say 250. And here it says 250, say 255. So the elevation of walking from point A to point B, the slope of this point becomes 255
minus.
Sorry, becomes 255 minus 250 divided by 20 minus 0.
0, yes.
And that will give you 5 over 20, which will give you 0.25. So this is 0.25. So that is the elevation, the slope. So if you are laying a pipe here now, a water pipe here, if I'm laying a water pipe here now, it means this water pipe will be at an elevation of, say, that. There's an elevation of 250. That's just what it is. Okay, Robert, you have a question. Go ahead, please.
Yes, I have just two questions. The first one would be these elevations. I mean, they have been taken from the surveyor from the surface.
Yes.
At what point we actually considering that the pipe will not be laid on the surface, it will be laid underneath the ground, is my first question. My second question is just on the Q per knot. Like, I can, of course, I easily understand the demand or the overall demand, but how do I do this division of that I know my Q for each knot? Okay. Yeah, those are my two questions.
Beautiful, beautiful. Your second question was supposed to come later on, but I will also put it now. The first question, if I remember, is on what's the first question again? Sorry.
It was the elevations.
The
they
elevation,
are from the ground.
Okay.
They were from the surface, and but the pipes are underneath the ground, which brings me to the next question. Also, again, how deep should be a pipe into the ground? Yeah, and when do we consider this additional? Maybe if it's 1 meter, 0.1 bar, basically, or we basically not caring about it. I don't know.
Okay, thank you very much. Now, for your design, you are going to use the surface as a reference. You're going to use a surface. Then you now take an offset. So the survey data you have are surface data. So you design your pipe as if they're going to lay on the surface. Then when you're now doing your computation, you now take an offset of between 600 and 1.2 meter. That's our standard here. But in Europe, because of snow and freezing, you can go as deep as 2 meters. But here in most parts in sub-Saharan Africa, Depending on if it is crossing a roadway, depending on the overburden, it should not be less than 0.6 and it should not be more than 1.2 for economic reasons. But in some cases, it can be more than that, but you must consider the economic of laying the pipes. So between 0.6 and 1.2 is what we normally use here. I stand to be corrected. If you have another opinion, you can give me. But in some countries, the standard varies. In countries where they have issue of snow, the standards in some places specify you can go as deep as 2 meters, so that during freezing, during hot winter, the pipe or the content of the pipe will not freeze. Then when you are crossing a railway line or you are crossing a highway, the parameters changes. So that is, it varies. So there's no constant, but there's a range. Then for the second question, it's a very beautiful question. And when you want to calculate your Q, now this is very simple. Number one, the first thing you know for your Q is what is the water demand, which we call Q subscript W. Sorry, I don't know how to write the subscript W here. And your Q subscript W could be, let us use 100 liters per capita per day. That is your Q. Then from your table, which I'm going to show us, you choose a safety factor, or what we call peak factor, hourly peak factor. For me, I normally use 2.2 as my hourly peak factor, but the hourly peak factor, it usually varies from my DVR standard between 1.3 to 2.5, depending on the population equivalent you are designing for. So you can choose any of these peak factor. Sometimes in Abuja, when they designed Abuja, they used 2.3. They chose 2.3 to design Abuja for 1 million population equivalent. Then the next thing you do is to know your PE, population equivalent. How many people are you designing for? So these are the 3 parameters you need. So to get your Q, your total Q becomes the Q of one person, which is 100, multiply by the peak factor. In this case, let me use 2.0, then multiply by the population equivalent, which we don't know for now. So if you're designing for 1 million people, you put it there, that becomes your Q. So the idea is, for instance, if I'm living in a house and we are 10 people in a 3-bedroom bungalow, the water demand per person will now be 100. Okay, and I'm designing for one house unit, and I say there are 10 persons or 10 capita. Okay, and based on the safety factor, which is going to be higher, because if you are designing for a smaller number of persons, use a higher number. I'm going to show us that. Let me say I'm choosing a population equivalent, a safety factor of 2. Therefore, the total Q at that point entering my house will be 100 multiplied by 10, which is multiplied by 2, then multiplied by the PE, which is 10%. So it means I will be needing 2,000 liters per day. So that is the demand for that house. A household of 10 persons in a day requires 2,000 liters, which is the same thing as 2 cubic meters per day. Remember, I say per day. But when you now want to design the pipe, you have to convert this into liters per seconds. And to convert liters per seconds, remember, you have to divide by 86400. And why do I get 86400? 1 day is 24 hours. Stay with me, please. 1 day, we have 24 hours in 1 day. And we have 60 minutes.
We can't see what you are writing anymore. It's too low.
Okay, sorry. Can you see it now?
Yes, thank you.
Okay, thank you. So A6400, some of us will remember our engineering days, engine 309, hydraulics, to convert day into seconds. then multiply by 60. So if you multiply these three parameters, you're going to get 86400. So if you divide this 2000 by 86400, you're going to get your flow in liters per second. So that would be 2000 divide 86400. That will give you 0.023 liters per seconds, which is the same thing as 2000 liters per day. These two are the same. So Robert, did you get it now? So
well, I get it very well, but the question was not to calculate the total demand, which I think is pretty clear. The question was, how do you split the total demand for each of the, in your table, you said we need to fill the queues for each knot.
Okay, we're going to do that now.
This was the question. But if you say we get to this later, we can move on.
It's exactly what we're going to do the next. We're about doing next. Okay, just hold on. Let me. So what I want us to do now is, can we open this chart? Everyone, can we open the table, the assignments? Because we want to do some calculation now. Can we open this? You have it here under your training workshop manual. You see workshop files and data. Can we open that quickly? And I have a question. Have we shared it before? Yes, I've shared it. Somebody said I didn't have it. Okay, let me bring it up now and share. So just give me 1 minute. Let me bring it up and I'll share with us, please. Okay, somebody say, are the points generated by going from top to bottom? No. I don't understand. Please, can you look yourself and ask me? I don't understand what you mean, please. You can unmute yourself and ask me what you want to.
Okay, good afternoon, sir.
Good afternoon.
Yes, sir. What I mean was that the points from the storage to 1, 2, 3, like that, the points, how are they generated? How were they come about?
You mean the survey points?
Yes. How were they come about, as in from the storage tank? How do I know? I know 1 is the storage. Then to 1. How do I know 1 is 1 and 2 is 2 and 3 is 3?
No. They are used arbitrarily. There is no. It's just your convention you use.
It's okay.
Sometimes it might not be like that. It could be those 1 and 2 could be the elevation points.
Okay.
Yeah. Sometimes they could be the elevation points.
It's all right. Thank you.
All right. Welcome. Any other question, please?
Yeah, I have a question. You explain the depth of pipe when excavating and backfilling. You said we mostly use 60 to 120, I guess.
Yeah, 0.6 meters to 1.2 meter. Yeah, is the safe. Is depending. This is in design we have lower boundary, we have upper boundary, and we have safe boundary. Now, depending on the terrain, you might not have a choice but to go down to 2 meters or 2.5 meters. Like I said, in Europe, because of freezing and winter, they go very deep. And then maybe because of for you to achieve a gentle slope, you might require to go too deep, but then you must consider the cost of going too deep. So the safe depth is between 0.6 meters and 1.2 meter. So if you are getting to where you are crossing road, you go as deep as 1.2 meter. But if you are going to maybe a bush part or a normal part, 0.6 is efficient. Then again, if you are going towards maybe where they are going to have a lot of field work or something like that, you might also consider going deeper, maintaining at 1.2, so that if they are doing bush burning or they are doing any activity on the surface, it will not affect your pipe down.
Okay, I understood that explanation. What I was trying to ask is, do we consider flow pressure or pipe diameter in such cases? Because, you know, when we are burying the pipes, there is no anchoring of these pipes. And then maybe because of some pressure, if we consider 0.6 meters, and the pressure tends to be, it can bring out the pipe from the ground level, especially in case of pumping. So I don't know, do we consider that, or is it's just about considering terrain and that's all?
Yeah, that's a good question. For some pipes, some pipe has some pressure, a maximum overburden that they can take. And these are usually specified in the pipe. And if you are using a bigger diameter pipe, we are looking, what we did, distance we are giving is not the invert from the bottom, but we are looking at the overburden. The overburden must not be more than 1.2 so that you don't suffer, break, the pipe will not break, or it will not suffer any structural defects. So that's what we're saying. So for the bigger diameter pipes, definitely you have to go as deep such that the overburden will be adequate to provide for some level of protection. I don't know if that answers your question, sir.
Yeah, thank you very much. It's okay.
Okay. So what I say we should do is for us to go back to this material and establish this, because the next point we are going to do now, which also Robert is asking, is how do we determine the Q? So to determine the Q, the first thing you do is when you are given this layout, you come up with a simplified network like this. So before I give that, let me explain what happens in water reticulation. And I'm going to explain it with on my whiteboard.
So I can't find that table in my material.
Okay. What you need to do is, if you go to, do you have this material that says workshop files and data?
Yes, sir.
The first PDF inside it, this is the first PDF.
Okay, sir.
So there are 3 sheets inside. The last sheet is the table.
Okay.
Okay. Now I need to explain something a bit now. And it's something that's very common in all spheres of engineering. In a water network, when you have a pipe, just stay with me, let me erase this. So when you have a pipe like this, bringing water from, let's say, from a tank.
So it's not among my materials. It's only the contour map that is there.
Go down. No, I'm sure if you go down.
It's just one sheet that I have there.
Okay. Okay, then be patient. I'll send it to you. I'm sorry about that. Okay, so if you have a water coming from a tank this way, and when it gets here, it branches, sorry. When it gets here, it branches this way. And then it branches this way. Just stay with me. Then it continues and branches this way. And then somewhere here, it branches this way, branches this way. If this water tank has initial water content of say 100 liters, or the flow from the tank coming is 100 liters per second. When it gets here, there are 3 branches here. It's possible that here will become 30, here becomes 40, or let's say here becomes 50. Here will automatically be 20. Then this 50 continues. And when it gets here, it drops 10 here and drops 20 here. Automatically, sorry, drops 20 here. Automatically, here must be 20. So that is how it works. So I want us to understand this analogy. So why is here 10? Why is here 20? It depends on the number of house connection here. It depends on the number of users here. So if I have 10 houses here and each house consumes 1 liter per second, it means here, it means that this place will probably have 20 houses. If here has 10 houses and they are all uniform. So it means if peradventure I removed this 20 and I ask you what is going to be there, all you need to do is to say, because this 50, when it comes here, it maintains that 50. Then when it now comes here, it shares this water based on the demand. So if I ask you now, what is the base demand here? You say it's going to be 20. But the base demand here will be 50. The base demand here will be 30. The base demand here will be 50. So you can see that between here and here, you still have 50 here, you still have 50 here. Why? Because there is no other branch here. There is no other house connection, or there's no other distribution that is taking the water. So I want us to understand this. So this is what we're going to, this is how it's going to be. So with this, you find out that as this pipe is coming down, it will be reducing in sizes. It will be reducing in sizes based on the base demand at every node. So let's put this into practice. Sorry. Here is node 13, and here is node 6. We cannot use land use because this place is already a developed area. We're already given the layout, number of houses. So what we're going to do now is we're going to count how many house connections are connected to this node. So here we'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. They are up to 25. I've done it severally. So the water demand at node 13, which is here, is going to be the whole
It's
house.
not the same thing showing on the screen.
Okay, sorry. I'm sorry about that. So let's come back here now. If you look at this node now, this diagram now, you find out that this is node 13. Look at it here. This is node 13, and this is node 6. So how many houses are here? So between this point and all the way to this point, how many houses are there? So I count them here. I discovered there are about 12 this side, 13 this side. That makes it 25 number of houses. So it means that the node here, the water demand, is going to be the demand of all the houses connected to it. Now, somebody will argue, in real life, if a pipe network is passing through this axis, the houses will be connected each other to that pipe. But in modeling, we assume that all of them are connected at one point. And if you agree with me, in a layout or in an estate or in a district, when you come to the beginning of the streets, there's supposed to be a metering system at that point that will meter all the people living downstream. So if I put a metering system here, for instance, or here, this metering system is taking care of all the waters, all the demand of all the interconnecting node houses here. So the first thing I'm now going to do is I will establish the value for one house. So I will come now and say, what is the house types? Just like my colleague said yesterday. So let's say the house type is 3-bedroom. Each of those houses is like a 3-bedroom bungalow or 3-bedroom houses. Okay. I'll now tell myself, what's the occupancy rate? What number of people in a house? So let me assume 10. My colleague was talking about 5. But because I'm designing for 50 years horizon, I will assume that based on population growth, based on development, by 50 years time, that is going to be accommodating 10 people. So I'll use 10 for my calculation. So it means there are 10 occupants or 10 capita, 10 people per house. And we all agreed yesterday or this afternoon that the water demand per person is 100. Simple calculation. If one person will take 100, what will 10 people take? 10 people will take 100 multiplied by 10. Then I'll increase it by my safety factor, or what I call peak factor, which depends on a lot of things, which we'll discuss yesterday. So let me assume that the peak factor is 2. Peak factor is to assume for fluctuation, for differences, or for change in use, or in fact, generally in engineering, we always multiply our final values by a certain peak factor. Okay. So here I will choose 2 for ease of calculation. For ease of calculation, I will choose 2 as my safety factor. So what does this tell me now? It means that for each household, each household along that corridor will be requiring 2,000 liters per day, sorry. Remember, this 100 is liters per capita per day. So by the time I multiply with 10, the capital will be eliminated. So I will now have 2,000 liters per day. That is what 10 people needs. And for those of us that have been to consultancy, you can relate with it. For a house that has 10 people, provide them with 2,000 liters gallon, 2 cubic meter gallon. That will what to do for them. Yes, that's the standard. They might not finish it, but that is the standard. So the next thing now is to calculate, to convert it to liter per seconds. Okay, so to convert it to liter per seconds, what do I do? I will divide that day by 60 by 60. So what do I do? So the day now becomes, the total value becomes 2,000 divide 86400. And that will be what? 0.023 liters per seconds. That is for one household, 1 unit. But in our network, we have 25 house connections connected to node 13. So if tomorrow I want to audit, all I need to do is to come to node 13 and I'll measure and check the flow and make sure that the flow is the flow for 25 people. So if one house so this is node 13 and it has 25 houses on both sides. So it means for me to get the total number of the flow that will service or that will be adequate for this 25 number of houses, all I need to do is to multiply my value by 25. So it means for node 13, the demand at that point will now be 25 houses multiplied by the value for one house. And we have calculated the value for one house to mean 0.023 liters per seconds. What it means is that for people to have water all around the day, there must be a flow of 0.023 liters per seconds flowing into each house every second. It makes perfect sense. Then for 25 houses, they will now need to, we now have to aggregate it. So let me multiply that out. So we have 25 multiplied by 0.023. And that will be giving us 0.58, 0.58 liters a second. So this is what you need in node 8. So what I will do now is I'll go to my chart under node 8 here. I think I have the Excel. Let me look for
was
the
it
Excel.
on node 6 to 13 we were looking at, not node 8?
Yeah, you are looking at section 6 to 13. That's a good
Yes,
question.
section.
Yeah, you are looking at section 6 to 13, but the node is at 13.
Yeah.
Yeah, thank you. The node is at 13.
Okay.
Yeah. So this is section 6 to 13. Look at it here. Okay. It has a distance of this. The elevation is 252. Now we are now computing for the Q. So after getting the Q, we now go to our chart and get the diameter. And that is the end of the design. So we're getting the Q now. So the Q, I will now come here. And
we are still showing. Hello, we are not seeing what you are doing.
Okay, sir. Sorry. I keep moving from my whiteboard to there. So I will now go to my Excel, for instance. I think I need to put this into Excel. I think I have it somewhere. If I'm to look for it, I don't know if it will take so much of my time. I know it's somewhere. And okay, let me quickly create one. So I have, that will take me some time. Okay, let's continue. Let's understand the concept. Okay. But I need to, just hold on, just stay with me, please. Okay, let me just put it this way. So node 13, the Q is what? 0.58. Just take note of that. The diameter, don't know the diameter. The length, and this one is the elevation. These are the 4 parameters we need. The demand, the Q, or let me say the demand, let me call it the demand. Yeah. It's that. It's Q, BQ. The diameter is a symbol like O. Maybe later I can get it. I'll get it from, then the length is meters, and the elevation in meters. Okay, so let's continue. So the node here is, so node 13. So the next node is node 6. I have to do it sequentially. So the next node is node 6. And so what do you have in node 6? In node 6, how many houses are connected to node 6? This is node 6 here. So upstream of node 6, you have 1, 2, 3, 4. You have like, sorry. We have, this is node 6. So upstream of node 6, we have 1, 2, 3, 4. We have about 4 houses. about 4 houses on node 6. Okay. Engineer Peter Omar and Engineer Joshua Aminchi. There's a chat. There's a response to your question. Just check your chat, please. So here you have node 6. Check your chats, Joshua Aminchi and Peter. So here you have node 6. So you count how many houses are connected to node 6. In my own case, I have 1, 2, 3, 4. So 4 houses. But because I'm a design engineer, I expect that in the future, there will be another number of houses here. So I can also decide to increase it for another 4. That was what we're talking about, future development or population projection. So even though those houses are not built now, but I expect them to be built in the next 50 years based on the layout. So I'm going to incorporate them in my design. I'm going to project and say in 2, 3, 4, or 10 years or 20 years, these houses will come on board. So why in my design today, I'm already going to incorporate the water demand they will need, provided I have the layout and know the kind of houses are going to come there so that I can capture appropriately their water demand. So for this case now, I'm going to assume 8 houses. So I'm going to assume another 4 houses. There are 4 houses this side. So I'm going to assume another 4 houses the other side. So for node 6 now, stay with me. I know it's a bit complicated for some of us, but I'm going to give us a table where I've solved every one of them. So for node 6 now, for node 6, number of houses is 6 houses. There are 6 houses. And the occupancy per house is 10. So the population equivalent of node 6 is going to be 60 persons or 60 PE. So when I come back to my formula to get the Q at node 6, it will now be the value for 1 multiplied by my safety factor. No, multiplied by the population equivalent. In this case, 60. I can also say 10. I can also use the value of 1 and multiply by 8,000. So I can also just stay with me. I can also say 60 multiplied by 10 multiplied by 60 multiplied by 2. That will give me the value for node 6, and that will be 12. That will give me 12,000 liters per second. And 12,000 liters per second is equivalent to 12,000 liters per day, sorry. So that will be equivalent to dividing it by 8,400. That will give me 0.14. 0.14 liters per second. That's the value. But I can also avoid this headache. Since I've established the value for 1 house, remember per unit, 1 unit is simply 0.023. So all I need to do is to say 0.023 multiplied by 8 houses. It will give me exactly the same value, the same figure. So what's the point? 0.023 multiplied by 8 is giving me 0.18. Sorry, this is 0.18.
I'm excited 50 now.
Are you using 6 houses or 8 houses? Like
Thank
you're
you.
using
Yeah,
between
yeah,
6
yeah,
and 8?
yeah, yeah, thank you. So here will be 8, sorry. Yeah, 8. So that will change.
That changes
this.
that value, yeah.
16. Yes. So I'm just trying to show you. Robert, are you okay? Did you get it now, please?
Well, it depends on what is your next step. Are you
Okay.
now Are you
Okay,
now
okay,
basically,
hold on.
if you put in your Excel only the amount for not 6, or
can
you
you-
add
Can you
the,
add?
the
Can you hold on? Hold on, please. Sorry,
yeah.
sorry.
Okay,
sorry.
so now it gets
I grabbed
interesting.
You. Yeah, I guess I understand where you're going. Just hold on. Now, remember this analogy I gave us. Can we understand this analogy? That if there are 50 here, I say here is 20 here. Remember this analogy I gave us. As you are, this water is coming as 100. Just hold on, stay with me. Good. Let me move this. And move this. Good. Good. All of you can see that when I came here, the first thing I did was to, first of all, calculate the value for the downstream. And when I came on board, I now added it to the value upstream. So for this value we have now, node 6, the value in node 6 now is now going to be the value we got, which is 0.18, plus the value for node 13, which is 0.58. Now, this is the tricky place, and I want us to understand it. And that was why I gave the analogy before I started, for you to understand so that you don't get confused. The value from every node, let me give this instance, for instance. I love to use this analogy again to explain. So let me use the analogy again to explain. Assuming this is a street. There's a house here. Just stay with me. It might look funny, but you're going to learn something from it. There are 3 houses here, and we have a water pipe passing through these houses. And everybody is connected to the house. Sorry. So this is house connection. This is a house connection. This is a house connection. And I'm supplying them with, say, 50 liters. 50 liters per second. Let's say here I have 15. Here I have, say, 25. And here I have, say, 10 people or occupants. The water demand at this point is 10. The water demand at this point is 35. Here will be 35. At this point, it will be the water demand, I'm just trying to explain something, will be 10. Then here, of course, the answer is already here. Here will be 50. That's how it goes. So it means that as this water, when this 50 liters per second gets here, the house connection, the district, the number of house connection, the number of the layout, the plan, the number of houses, the population density here takes a value of, say, 15. What is left will be 35 that will service 2 other districts or 2 other estates. And those 2 other estates are having I don't want to say number, but I want to say a weight. Let me use the word weight. It's carrying a weight of 10, and this one is carrying a weight of 25. So when it gets here, if I ask you what is the water demand at this point, you're not going to tell me it's 25. No. 25 is the base demand for this house. But the water demand at this pipe at that point is 35. So it's going to give this one 25, and it will move on to distribute the remaining 10. So I mean there are other houses remaining here. Okay, if I decide to add, if I decide to add one more house here, just stay with me. Let me remove this from the screen. If I decide to add one more house here, I can tell you this guy is not going to see any water. If everybody is demanding for water, except I reduce the value here by say 5, and now come here and then give him himself and then give him 5. Meaning that here will now be 5. This is where the trick, this is where it becomes tricky. And if you can understand how to compute and get the water demand of this network, my problem is solved. This is what gives people headache. The capacity, why this is important is that as the demand is reducing, that is how the pipe size will be reducing. So that is how you can do your economic design and it will fall into standard. Are you with me? Okay. So I want us to take note of this. Okay. So in this our network now, if I get the value of this point, which is not, oh, sorry, it's not showing. In this our network now, when I calculated the number of houses connected here, okay, and I got the value here as 0.58. When I got to node 6 here, there are about 8 houses upstream of node 6. So the demand of node 6 is not just the value for the 8 houses, but it's the value of those 8 nodes plus the value it is meant to supply downstream. I will just plead with everybody in this class to understand this. Those of you that are into, all of us are engineers. This same concept is obtainable in fluid mechanics, is obtainable in electrical, in current distribution, is obtainable in virtually every facet of engineering. In electrical, they call it Kirchhoff's law. They call it the Kirchhoff's law. In mechanical engineering, I don't know what they call it because I'm not a mechanical engineer. But to those of us that are civil engineers, we know that this is something that we often meet in fluid mechanics. Okay? In fluid mechanics, we call it law of continuity. That's what we call it in fluid mechanics. We call it the law of continuity, which says that A1 V1 must be equal to A2 V2 plus A3 V3. Are you with me? Plus AN, that's subscript N, VN. Sorry, small n. Small n. And before that sum, I must put ... Sorry. Just stay with me, please. I must put some dots here. That's the I don't know what I call it, law of continuity. Depends on where you're coming from. But please, gentlemen and ladies, I just want to understand this and then relate it with the network. So when I got 0.58 here, and I'm doing for node 6 automatically becomes its own value plus the value downstream. And that is why in my Excel sheet, node 6 becomes this. Look at my address bar, 0.18, which is its own demand plus the demand downstream. So downstream and base, the base demand and the downstream demand gives you the total demand at node 6. The next node we're going to compute is node 7. Before we go to node 7, we must get the value for node 11. because node 11, because node 7 is simply going to be node 6 plus node 11 to give you node 7. Before we do node 9, we must get the value for node 10 and node 12. Meanwhile, I would like us to ignore these dotted lines. This dotted line here is if you're using a looping. I will come to that later. The dotted line is for looping. If I'm looping, then it means I have to put a loop. Remember, I told us there are two different systems.
We can't see it, sir.
Okay, sorry. So the next thing we're going to get is node. This is node. Okay. Engineer, you have to open this file so that as I'm working, you're working. But unfortunately, you complain you don't have the file. So let me quickly share that file with you immediately, because it's important that you open it on your own.
Can you share on WhatsApp?
It's possible. Then chat me on WhatsApp then.
Okay.
Say me hi. Say hi on WhatsApp to me, please.
Please, I don't have also. I've said so.
Okay. Which of them you don't have? The entire material?
The entire material, yes.
Okay. Just say me hi on WhatsApp. I'll share it now. So this is my Google Drive. So I'll go to Google Drive. Then I'll go to the folder. The network's a bit slow. So I'll go to the folder in my Google Drive. And this is the folder. I'll right click on it and say share. Okay, just hold on. Okay, copy link. Okay, so there you go. Okay. Okay, this is Lukman, I guess. Shared. And
that's me.
Again. Okay. Shared. And go again. Who is 280? Balogun. Okay. Shared. And generate chat. Shared. Okay, so let's continue. So if you go back to our network, you will find out that for me to get node 7, I need to go to node 11. So how do you get node 11? I'll go back to the houses and know how many house connections are connected to node 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are about 10 houses. Okay? There are about 10 houses. So 10 multiplied by the value of 1. So for node, this is node 6 we just did. So we're going to do node 11. So node 11 will be, we've already calculated the value for one house. So it should simply be 0.023 multiplied by, Akosile, what's the question? Multiply by 10 houses. So that will give us 0.23 meters per seconds. And that will be the value for node 11 because node 11 does not have any downstream. It does not have any house downstream. So that's the final, that's an end node. Node 11 is now 0.23. And the reason is that it has only 10 houses. So somebody's hand is raised. Please, can you ask your question, please? So this is node 11. Any question?
You were saying? So what did you say the dotted line stands for again?
Okay,
sorry.
the dotted line is that if I'm looping, there are two types of system. You have a branch system, we showed this yesterday, and a loop system. And then both of one have advantage, the other one has advantage, they all have advantage and disadvantage. So looping sometimes helps you if you are doing water maintenance in one area, water will flow through the other area. So, but for now, for the purpose of this class, we are just focusing on the branch system. But I will make reference to the loop system, what you use. So even if you are designing a loop system here, what this thing simply represent will be a valve.
Okay.
You introduce a valve here, and introduce a valve here, meaning that this valve can be opened in case of maintenance. Assuming I'm maintaining something here, it means that water I can open this valve so that people in node 10 can get water through node 5. If not, they are originally supposed to get water from node 9. So water passes through node 10, 8, node 4, goes to node 8. At node 8, it divides into proportionally into 7 and 9. 9 divides proportionally into 10 and 12.
Okay.
So finally now, we have done for node 13, we have done for node 6, we have done for node 11. Now we are doing for node 7. And I said before you get node 7, you must have done node 11 and node 6. Okay, so what will I do now? What will I do now is that for me to get node 7, I have to add up this value plus this value and see if there are any houses connected to him, to itself. I hope nobody's confused there. Node 7 will now be all the houses connected to it plus the houses downstream. Here, this is, let's assume this is node 7. It means node 7 has a base demand of 25. So the total demand at node 7 is the demand coming from node 11 and the demand coming from node 6, and then its own demand. So it means 3 variables, I'm going to do 3 computations, and I've already done 2. So I need to do one more computation. And that computation I need to do is this computation to know these 4 houses that are connected to node 7. This is node 7 here. And there are 4 houses connected to him. And if I do what I have done before, I will assume that new 4 houses will pop up in the future here. So I'm going to use the value for 8 houses. Are you with me? Yes, so for node 7 now, I'll do it somewhere here. For node 7, it becomes node 11 plus node 6 plus node 7. Somebody will say, why node 7, node 7? Because node 7 has a base demand of 25. For me to achieve 35, it means it has its own base demand and then add it to the 2 previous demands. I know it's tricky. I know. It is difficult for me. It took me a while to understand it. And you can agree with me, that was why Roberts wanted to mention it and say, calm down. I understand, because he himself already have an idea that is the most tricky part. And that is where most of our engineers are failing it. When they come, they'll use the same pipe size from 1 to end. No, the pipe size here might be, let's say 4 inches. Here, 3 inches. Here, 2 inches. And then 2 inches, because you can't go below 2 inches. So you use minimum what they call nominal pipe size. So if you understand this and you do your water design, you will find out that the pipe will be gradating based on the weight, based on the weight of the branching off. Are you with me? Any question? I expect someone to ask question, unless it's well understood.
Yeah, I have a question.
Okay.
I fully understand the logic of it, and you know, we fill the template. But when you say we need this to feed our Epanet system, is it? I was thinking Epanet is designed in a way that we can feed only basically maybe number of houses for each knot, and then it does the adding of downstream knots automatically. We don't need to worry about it. But it looks like this is not the case. We really need to do this manually, or is there actually in the course of our course at some point it's not actually necessary that we do it, or is there no way? Is there simply no way? We have to use our brain cells to actually make sure that we do the demand for each knot plus downstream knot.
That's correct. We have to do it. Epanet is a very old software. Some new softwares have come on board that can do that, but they are very expensive. I know in Germany they have Rhyme. They have a software they call Rhyme. The last time I was in Munich, they have it, but it's very, very expensive. Now, then the people in Canada, I think they also have something like, I think in California, they have a water card. But some of those softwares, they will do most of the work for you, but they are very expensive. But for the Epanet, as you rightly said, you have to do this. You have to do this. You must do this. Epanet does not have the capacity to do it for you. You have to calculate the demand. Epanet is interested in the demands. But the good news is that when you do it to a certain level, you can move very fast. Because once you see, if you have done for 20 houses and you see 15 houses, come on, you just use the value for 20 houses. So starting is difficult, but once you have done for like 10 samples, then you can just be keying in the value. It's easy for you to just key in the value. I don't know if you understand. Like if I produce a table to say 1 hectare, 2 hectare, 3 hectare, or 10 houses, 20 houses, 30 houses. So my job will now to say, if it is less than 30 houses, if it's between 20 and 30 houses, I'll use the value, I'll use a point value. If it's between 10 houses and 20 houses, I'll use a point value, just like we do in our structural design. Okay, those of us are civil engineers. When you do a 5-meter beam and you do a 6-meter beam, I mean, we all know that we just go for the parameters for the 6-meter beam and use it on the 5-meter beam. That could be a little bit of over designing, but for ease of calculation and for you to be fast. So you are right, Epanet does not make provision for you to key in houses. We are hoping that in the next few years, more softwares that will be open source, because there are software that can do that now, but they are not open source. They are difficult and they don't fall within our policy. Our policy is always to use free softwares. All our training in Vasa and Bao, we make sure we use open source software because we know they are easy, they are accessible, and of course they are cheaper. Okay, I don't know if that answers your question. Engineer Ezugu said, if a particular node has water demand more than the other nodes attached to it, what will be the pipe size? We'll come to that. Let's not jump the gun. That's a good question. What you just asked is here, if a particular node has water demand more than the other node attached to it, just like here you have node 7 being attached to node 5 and node 10, you could see that the total demand becomes 35, which is 5, yeah, which is 5 plus 5 plus itself, and that gives that 35. And here, it has a lower demand than the previous people, yet the demand at this point is still 50, whereas its own base demand is 15. So this does not mean that you have a small pipe size here and a big pipe size here. No, rather the opposite is the case. Any question?
Yes, I want to ask something about what obtains in a fairly big city. I think what we are doing is okay for a small community where houses can be counted. But what happens in an urban area where you have so many properties that if you have to start counting the houses to determine the demand at the nodes, then you will spend more than a year or years even in doing such counting. How do you go about doing that? Thank you.
Thank you, sir. That question came up yesterday. We talked about two methods. Is either you use the number of houses or you use the land use of that area. For a virgin land, for a virgin development like Abuja, when Abuja was designed, Abuja is one of the few cities that was designed from the scratch. When the concept of Abuja came on board in the early 70s, there were virtually nothing in Abuja. Abuja was just a virgin forest, a virgin land. So what they used was they now designed Abuja based on land use. Some places they say this is going to be low density areas, this is going to be medium density areas, this is going to be high density areas. So that word density is an indication of the number of houses, which also is an indication of the type of infrastructure to be provided. That's why if you come to Abuja, we have central area, we have phase one, we have Maitama. When they are designing the city, the places that are high density areas, they will assume, let's say, 1,000 people per hectare. For the medium density area, they will assume 500 people per hectare, per space. And for the low density area, they assume, let's say, 250 people per hectare. So if you go to density area and you want to build a 10-story or 5-story building, they will tell you, no, that place is a low density area. It means you have to build like bungalow or one floor. Then if you go to the high density areas and you want to build a bungalow, they will say, no, this place was designed to be a high density area. You can only build 4, 5, 6, 7, 8 floors because we have already captured based on the infrastructure, based on the pipe size we are provided there, we anticipate that for every 1 hectare, there's going to be 1,000 people. I don't know if that answers your question, sir.
Yes, thank you.
Okay. Okay, so now we have done node 7. So from here, you could see that we have done node 11, we have done node 6. Node 7 is equivalent to node 8 houses. So 8 houses is somewhere 0.18. Yeah, this is the value for 8 houses for node 7. So the total now becomes node 11. What do we have in node 11? Node 11 is 0.23 plus node 6. Node 6 is 0.18. Node 6, remember, node 6 is 0.58 plus 0.18. Does someone remember that? Then node 7 is now 0.18. I want somebody to ask me a question on this. If you didn't understand how I got node 7, please, this is a time for you to ask me. If we all understood it, then I'll be glad, I'll be happy. one point two liters per seconds. That's the value for.
No, it should be, isn't it 0.99? 0.76, which is the sum of 0.18 plus 0.58, which plus then the 0.23 from node 11.
No, sir. I think it's more than that. It's about 0. Check it again. We have 0.23 plus 0.76, yeah? Plus 0.18 is 1.17, which is approximately 1.2. Remember, we have houses attached
yeah,
to node.
yeah. Ah, yes.
Yeah.
Okay. Ah, yeah.
Okay.
Correct.
Okay.
Correct.
Thank you. Okay. So node 7. This is node 7 becomes 1.2. The next thing I'm going to do is, remember, I'm going to do for all the nodes. So somebody will say, this is difficult, this is painstaking. Just hold on. It's not that difficult, because very soon you will see me making assumptions, reasonable assumptions. Okay. You will see me when I've done like for like 5 or 10, I can easily pick values. So now node 12, you're in node 12 now. How many houses are in node 12? So let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9. You simply assume 10. This is what I always tell my participants in my training. In infrastructure design, it is better you over-design than you under-design. I'll say it again. It is better to over-design than to under-design. Under-design is absolutely unacceptable. Over-design, okay, we're going to spend extra money, but it will work. But under-design might not work. Over-design will work, but it will be expensive. And if peradventure there's population explosion, it will accommodate it. So here I have 9 houses, but I have done for 10 houses. So I'm going to assume the value for 10 houses. Yeah. Remember, I'm on node 12. Look at node 12 here. That's why I said I want everyone to open this PDF on your laptop. It's important that you open it so that you can flow. You might not be writing, you might not be doing anything, but just understand the concept. The video is there for you to watch, but just understand the concept. So here, this is node 12, this is node 9, this is node 10. So node 12 has 9 houses. So if I have developed a template for 10 houses, which is 0.23, I don't need to worry myself again. So what I'll do, I'll simply come here and I'll say node 12 is 0.23. If you disagree with me, well, I'm a lazy guy. So the next, I'm going to go to node 10. So how many houses are node 10? One of our engineers just asked me, if you don't know the number of houses, then I can choose the area. What area is node 10 going to serve? 2 hectares, 3 hectares, half hectares, 2,000 square meters. How many houses will that translate to based on the land use? For every city, the first thing they do is to have what they call land use. The city must be designed based on land use. This is what we want this place to be: central area. We want here to be a residential area. We want here to be industrial area. So that place is industrial area, you can begin to calculate and know the number of workers or how you want to design it. Okay, you say, okay, node 2 is not looped. Node 2 is, that looping is if you are using loop system. We said there's a branch system and a loop system. So the dotted line is assuming you are using a loop system. It means you now continue with that line. And I said, in this case, if you do a branch system, what you do there is that you provide a valve there, a closed valve there. Okay. Now, node 10 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's also 10 houses. But let me draw your attention to something. If you look at some of these houses, they are bigger than these houses here. So, but we chose 10 people per house. So these houses might be double of this. If they are double of this, you must factor it in. You must increase the population equivalent. If this is a hospital, I will isolate it and then go to my table, which I showed you yesterday, and get the value for hospital and compute it and know that I'm not using the same value for this hospital, I will increase it by a certain factor. Did you get its place? Okay, can I take us back one step, sir? I mean, the line to when to node 12 is slashed. Yeah, I understand what you mean, sir, Engineer Elijah. Sorry, gentlemen, let me move back. This, I want you to eliminate this line, okay? You put this line when you are designing a loop system. Let me show us what we're designing here. Just stay with me. Chapter 8, no. Lecture materials. Remember, we didn't do chapter 8 yesterday. So chapter 8 will show you all what I'm doing today, the step-by-step approach. I'm just doing it practically without going through the first, without explaining how it is done, but chapter 8 will explain everything to us. Just stay with me. Okay, this is chapter 8 of our lecture yesterday. So this is what a branch system look like. Yeah, this is it. So this is what we're designing. This is what we're doing. Okay, this is exactly what we're doing. So these are node 13, these are node 6, these are node 7, these are node 11. Now we have done node 12. We have also done node 10. Node 10 and node 12 are the same. Both have 10 houses, even though this one have 9 houses, but I just, I lazily made it 10 to make it easy for me. And this one has 10 houses. So this is also 2.3. This is 2.3. So the value for node 9 will now be this plus itself. This plus itself. So node 10 is going to be 0.23. Node 9 is going to be what? Can somebody do it? Can somebody try to do node 9?
I think it's also 0.23.
Are there 10 houses in node 9?
Yeah, we counted.
That means the total houses will now be 0.23, 0.23 plus 0.23. So let me check. No, sir. This is node 9 here. We have only 4 houses. 1, 2, 3, 4. So 4 houses will be what? We've not done anything on 4 houses. So 4 houses will be, hold on, just hold on. So we're talking at node 9. Watch me now. Watch this. Node 9. Node 9 will be node 10. All right. Node 9 will be node 10 plus node 12 plus itself. This is node 10, this is node 12, and this is node 9. So node 9 will be node 10 plus node 12 plus there are 2 houses, 4 houses along here. Okay, so what we're going to have there now will be so node 10 plus node 12 plus node 9. So what node 9, its base is already 0.9. Let me use the word, yeah, about that. 0.9. Therefore, the total will now be 0.23. Please, and please, if you know you don't understand it, please draw me back. I got my 0.9 by doing, what I did was to say 4 times. 4 times 0.023. Let me be sure about that. Oh, 0.09, sorry, 0.09. That will give us 0.55. That will give us 0.55. So here, node 9, what it made now is 0.23, which is the value for node 12, plus 0.23 value for node 10, plus 0.09, which is its own value. I'll give you 0.55. Zero 0.23 plus 0.23 plus 0.09, which is for the 4 houses attached to him. Any question? Is that well understood? Now we'll move over to node 8. Who can tell me the value for node 8? How do you calculate it? What node and what node constitute node 8?
Node 8 is
Node 7.
node, yeah, it's basically node 13
7.
plus node 6 plus node 7 plus node 11 plus node 12 plus node 9 plus node 10 plus itself.
Or you simply say node 7 plus node 9. Why?
Plus itself. Yeah.
Plus itself. Yeah. Why?
Exactly,
Because
yeah.
node 7 is I've already captured the downstream. Yeah. So
Yes.
now, is there any houses to nodes? There's no houses. So there's no houses between sorry. There are no house. Okay, we are node 8. It does not have any house on itself. So node 8 is automatically node 9 plus node 7. Any disagreement? Node 8 is going to be equal to node 9 plus node 7. And that will be 1.75. So let me save this. I'm going to upload it to us. Let me save this file. I'm going to share with us because tomorrow, that's what we're going to be used for the computer model. Just to introduce us to the computer model. So let me save it well. Here's that material, Epanet. Wow. A lot of programs are here. Excel. For Epanet. Okay. Okay. I think it's been saved. Somebody asked a question. He said, please consider from the beginning point, which is node 13. I thought node 9 is node 8 plus node 12. Yes. No. Node 9 is node 8 plus node 12. Node 9. No. Node 9 is node 12 plus node 10. No. Okay, don't be confused, man. You know, when you come to node 8, node 8 has 2 branches. So these 2 branches are independent. One on your right, one on your left. So the mother branch is node 8. And the water is coming from ST. You have to take cognizance of where the water is coming from. The water is coming from node 4 to node 8. So node 8 will now distribute to node 9 and node 7. So the person that has, that's why node 8 now is 1.75, while node 7 is 1.2, and node 9 is 1.55. So if you add 0.55 plus 1.2, you're going to get 1.75, and that is absolutely right. Next, we're going to do node 4. Before we do node 4, we need to find the value for node 5 and node 3. We already have node 8. Am I right? We already have node 8. So we're now looking for node 5 and node 3. Now, this brings into play one of the questions that one of our engineers also asked. If you look at note 5, some houses are not bearing the same shape like this. And what did I say? I said those houses have to be isolated. You design them for what they are, whether they are in factory, industry, hospitals, hotel, school building, football field, farmland, and whatever they are. You need to isolate them, calculate their water demand, and then add it to total. And that will probably push the whole thing up. For instance, if you look at this building here, this building is like almost 4 in 1. So what smart thing I'm going to do is this. After counting these houses, I'm going to add 2 extra house number to it to make up for this bigger house, which could also be bigger in space or can be something that is out of the blues. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 houses. But because this house looks big in size, I will also assume that the occupancy or the number of persons occupying it will also be as big as that. So I'm going to add 15, 14, 15. So I'm going to design for 15 houses for node 5. Any question? So for node 5, I think I have something I'm going to share with us in Word. I think I have something where I've done some of these calculations. Let me check. I think I'll share something with us after the class. Yeah. Okay, this is for the sizing. I think I'll share this with us. Yeah, node 6, 8 houses. Yeah. All the things we are doing now is already in this Word document. So I'm going to share this Word document with us. And I suspect it's already with us anyway. I strongly believe some of us already have it. So it also shows you how we got to node 12. For instance, we are on node, where are we now? We are on node 6. Yeah. So this is node 6. Only that we choose a different value. Yeah. We assume, yeah, it's here. It's here. So there's no problem about that. So we are node 5. So node 5 is going to be 15 houses multiplied by 0.23. Those of us that are just coming for the first time, 0.23 is the value we computed for one house, and you all know how we got it. The water demand times number of persons times safety factor. So it is giving us 0.35. 0.35. So that's the value for node 15. Then we move to node 3. So node 3 again. So node 3 again is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But this one look like 4. This one look like 3. So I'll assume for 20 houses. Or let me just assume 15, not to confuse you when you are going through it. But take note. While you are doing your design, you must do it that way. Is that understood? Engineer John, please check your message. Thank you. Okay, so we are now on node 3. So node 3, we have computed node 3. Node 3, from what we have computed, is let me go back to sharing. Or rather, the white screen. So node 3 is this. Just hold on. Select. Good. So node 3 is going to be 15 houses, which I said in real life you have to multiply by 20 to make up for the ones that are huge. Okay. So that is be 15 multiplied by 0.23, 0.023 times 15 equals okay, the same value, 0.35. Okay, so I want us to finish this in the next 5 minutes. So I can go and design the pipe, and that will be the end. And then detailing is something we can discuss later. So this is 0.35. So back to my Excel. Node 3 is also 0.35. Therefore, node 4 is going to be what? Equal to node 3 plus node 5 plus node 8. 2.445. Any question about that? That's node 4. Then node 2. What's the value for node 2? Node 2 has 5 houses and 1 empty plot here. But let's just assume 5 houses. So 5 houses will be 0.12. Okay. So node 2 is 0.12. That's very simple. Node 2 is 0.12. No, 0.012. Yeah. 0.0. Am I right? No, 0.12. Therefore, node 1 is going to be what? Node 2 plus node 4. $2.57. Because there are no houses between 1 and this, it means the storage tank will also be the same. There are no houses between here and here. Oh, I made a mistake. Sorry. This is node 1. This is node 4. I need to add 1, 2, 3, 4, 5. Then if I mirror it, it will be 10. So I'm wrong. So node 1 will be this value plus the value for those 10 houses, which is 0.23. And that will give me 2.8. That will give me 2.8. So because there are no other houses there, the storage tank becomes same, 2.8. 2.8 liters per second. Take note. Now, somebody said something yesterday, somebody from C&A Consultant, I think it's a Shitu or so. Now, you can use this now, take it back to liters per day. That will give you the size of the storage tank for 1 day storage, 1 day pumping, 1 day pumping, 24-hour storage. Did you understand that? So if I convert this 2.8 is in liters per second. If I convert it to liters per day, that will give me an idea of the size of storage I need for 1 day if I'm pumping only once. In other words, at the storage tank, if I don't want to apply the formula we used yesterday, which is equalizing volume plus consumption demand plus firefighting, you say that's the standard way of doing it. But to check myself, I will say the storage tank is 2.8 liters per second. This is the total number. If I multiply it by A6400, 2.8 multiplied by 86400, that will give me the liters of water of the demand of the entire estate, of the entire design. 2.8 multiply 86400. It will give me 241,920 liters per day, or 241 cubic meter per day, whichever one you use. These and these are the same. So if somebody asks you, what is the water demand of the entire people, of the entire estate, this is how I will do it. And I can also do it by coming here and counting the number of houses here, multiply it by the value of one house, I will get it. If I multiply the number of houses in here now, and multiply by one house, the number of houses here are about 100. So if I multiply 100 by it, I also get the same value. But the problem will be, I won't be able to get the appropriate pipe sizing that I will use for my design. So if you come here now, you will find out that the pipe that will convey water here and the pipe that will convey water at node 4 cannot be the same. So now we move over to the, remember we have all this. This is given. All these ones are given. Okay, they're all given. Okay, the elevation given. Okay, let me not confuse us with this. So you can see that I said we need 4 parameters: the demand, the diameter, the length, the elevation, for you to now do your network analysis. So what is left for us now is to do the pipe sizing. How do we size the pipe? So that's what we're going to do now. We're going to do the pipe sizing. And to do our pipe sizing, we are going to go to our charts, our nomogram charts. Okay, we're going to go to our nomogram charts. So in our nomogram charts, what you do is you go back to this folder called workshop files and data. By the way, do we have this estate design? Maybe we don't have it. So let me upload it in that Google Drive. Let me quickly upload it here so that all of us can access it. So if you access the Google Drive again, you'll see it. I don't think it's there. It's not there. So let me upload it for us. Upload file. So I'm going to upload something in our Google Drive. So go back, visit the Google Drive again. You see in just a minute, if you visit the Google Drive, you're going to see a new uploaded stuff that will, all this I'm doing on the whiteboard are all there already. Sorry. Good. So go back to your Google Drive. You'll see a new file I have uploaded called ABC Estate Design. So it will show you all the things we have done today. Node 11, node 12 is this. Node this, how we got it. The only difference is that we assume 20 number per house, whereas today we assumed sorry, let me just take a look again. Okay, I think it's same. Just take notes. Everything is now here. So the next one we're going to do now will be the pipe sizing. So let's size the pipe. So to size the pipe, you open your table or your chart. That is what you use in sizing pipe in engineering. Chart or table. But in my own case, I have a chart. A chart by Kolebru Pandi, developed by the University of Stuttgart. If you go online, you see a lot of charts. You can use any one, and I can bet you get the same results. Now for the charts, we have 3 charts. So we have 0.1, we have 0.4, and we have 1.0. 0.1 is for PVC pipes, very smooth pipes. 0.4 is for ductile iron, and 1.0 is for concrete iron. So let me try something out. So for instance, if you go online and you say, well, just watch me now. If I go online now, anywhere online, I'll say Google, and I'll say frictional factor for pipes. I just want you to take a look and see that sometimes some of these things are already in open domain. Okay, it's coming. It's coming. If you type frictional factor, it will bring you hundreds and thousands of them. It's not coming up. So let's just continue until it comes up. So here I'm going to use the nomogram written 0.1. Sorry, my system is I don't know. Okay, it's coming. I'm trying to open it with PDF. Meanwhile, while I'm opening it, please, can you open yours too? Nomogram for 0.1. So we're going to use PVC pipe. Okay, this is what the pipe looks like. Down here, you see the pipe is in the losses. Now, every pipe in the market has 2 parameters for every pipe material. They must specify the frictional factor, which is a function of the head loss, and the bar, the pressure it can withstand. Every pipe must indicate the pipe the pressure of the pipe, the maximum pressure can withhold, and the frictional factor. So here you see that on the horizontal is the flow, the discharge, the Q, which you must get first. On the horizontal is the slope. The slope is in horizontal. And let me say this, the slope is in per kilometer. The slope is per kilometer. That is why if you look at this symbol here, it says 0/00. So when you get a slope of say 0.25, that 0.25 means 0.25 per kilometer. It means 0.25 per kilometer. So if you are using meter as your measure, it means you have to multiply by 10. Hello? I don't know how to explain this, but this chart is in per kilometer. I don't know, I think it's written somewhere down here. Per kilometer, it's not here. Yeah, look at it here. Okay, no. I know it's just somewhere well written in per kilometer. So 0.25 per kilometer.
I think from my understanding, it's basically the same unit as a percentage. It's called, I think it's called promille, which is basically a factor 10 smaller than a percentage, just to
10.
make it probably, to avoid having 0.4 or 0.3, to have a nicer basically scaling by a factor of 10. The difference between percentage and promille.
Yeah. So okay. So what it means is that when you get your slope, you have to multiply by 10 to read this chart. Is that what you're saying, sir?
Exactly. If you calculate your slope,
no,
and yeah, exactly.
Finish.
If you calculate your slope in percent, like we basically naturally do, we multiply then
by
if
10.
you have by 10 to get, and then to use this scale. Yeah.
Thank
exactly.
You. That's perfect. So let me just say this, generally speaking, for every chart you want to use to do design, there are rules and laws that guides that chart. So for every chart you need to read you need to read about the chart. You need to understand the rule. Just like a psychometric chart. The first time I saw a psychometric chart, it blew my mind, because in psychometric chart you can get like 10 parameters in a psychometric chart. In our own case, you can impute 2 parameters, you get 2 parameters. So on my horizontal is the flow. On the vertical is the slope. So when I get the slope and I get the discharge, their meeting point will give me the pipe size and the velocity at that point. The pipe size and the velocity at that point. For instance, let's just start. Then for any value that is less than 1, I will use the value for 1. Let me give you an analogy of this. In design, some of you are in my class in sewer and stormwater design last week. In sewer and stormwater design, in sewer design, basically, the minimum acceptable pipe size is 150 mm, 6 inches. That's their minimum acceptable design based on German standard. That's the minimum acceptable design pipe size. So even if you do your design and you got 4 inches pipe or 5 inches pipe, the standard says you cannot use anything below 150 mm. So that becomes your lower boundary limits. So in this our own case, any flow that is less than 1 liters per second, you're going to use the pipe size for 1 liter per second. So that is why you see in most design, you see repetition. of pipe sizes, even though some of them are done on error. So what it simply means is that if I want to design the first slope here, remember I need to have the slope by my side. But for the purpose of this design, we will assume a common slope. Just for us to do this design, okay? Let's assume a uniform slope. But in real life, we are going to design the slope based on the difference between the elevation and the horizontal. Okay, so for this one, let's assume a slope of 0.5. For the purpose of learning fast, are we together? 0.5, no units, but we assume a percentage. That means using my charts, this is translates to 5 per mil. Are you together? So when I say a slope of 0.5, but if I want to use this chart, I'm going to read it up against 5 because the slope is in per mil, per thousand, per kilometer. So somebody's asking a question. You say you can't hear me. I'm afraid it's from your end. Engineer Oladele, when you log in and log out and log in, and then ask him to log in with your Wi-Fi and audio, computer audio. That's what causes that. Okay. So now we are going to size this pipe. So based on 5, what do we do now? I will come here. This is 1. I can't see 0.5 against 5%. So it will fall in between 2 pipe sizes. In this case, I'm getting myself somewhere here. This is 5. This is 1 meter per second. I go up and I come down here in between. And it's falling between 50 mm pipe and 65 mm pipe. The rule says you choose the bigger of the two because as engineers, we design based on worst case scenario. And as my philosophy also, I shared with you, in infrastructure design, it is better to over design than to under design. Under design is, in German we say, is verboten, is unacceptable. It's absolutely not acceptable. So here, what do we have? This is 5 per mil. So it's falling between diameter 50 and diameter 65. So I'll choose diameter 65. Then if you look down here, it's falling between these two lines going downwards. And that would be the velocity at that point. And here is giving me a velocity of 0.5. A velocity of 0.5. Yesterday, we said minimum velocity must not be less than 0.3 meters per second. So it means the velocity requirement is perfect or is fulfilled. And the pipe size is 65 mm. Engineer Ochimana, what's the question, please?
What if your pipe size is the pipe size from your chart? What if it's a size that is not available in the market?
You choose the biggest available one, sir. So in this case, you're going to choose 75 mm based on Nigerian standard.
Also, but are you going to go ahead and design based on 65 or based on the size that is in the market?
You put 65 as required and 75 as provided.
Okay.
I don't know if you understand those days we do design.
In reinforcement, we do that. When you arrive at 11.5, you go to 12 as
thank you.
Reinforcement.
Thank you. The same thing applies. In fact, let me even tell you, if you design and put 65, you've done your job. It is the contractor or whoever is doing the estimate that will, but it's good. You ask a good question, perfect question. You know, that's why in engineering, you also have to look at the local conditions and look at the standard. This chart was calibrated in Germany. In Germany, they have DN65, I guess. But we that are using British standard, until recently, that they've harmonized, I don't think we have 65 mm. Then what we have here is 50 and 75. But wait a minute. I think we have a 2.5 inches pipe in the market. Somebody answer me. People from C&A. Do we have 2.5 inches? 2.5 inches, yeah? Yeah. I can't hear you, sir. Can't hear you well. Put it in the chat box. Put in the chat box. Put in the chat box. Maybe it's running in Lagos. Okay, let's continue. Put in chat box. So if there is, that means we use 65. So let's go to the second one. So now the pipe size here will be what? 65 mm. Are we together?
Maybe when you do the next one to understand better.
Okay, good. The next one is the same thing. I don't even need to look at, since we're using the same, we're using the same slope. So this one is also 65.
No, I wanted them to pick it from the chart. So I will understand.
Okay, let me do for node 7. Let me do for node 7, 1.2. So let's go to 1.2.
Okay.
This is 1.5. So 1.25 halfway. And the slope is still 5. So 5 is still giving me the same. So for 1.2, I'll see you 65.
So I don't know how you got this 65. I'm just opening up my eyes and trying to get it with.
Okay, let me do it again. For the ones that are less than 0.1 liter per second, we assumed 1 as the minimum acceptable based on standard. So I will now read 1 now against the slope is 0.5. But we're going to read against 5 per mil because this is calibrated in per thousand. If somebody gives you 5, if somebody gives you 0.5 as a slope, if you upscale it to a factor of 10, it will be multiplied by 10. So here we multiply by 10. So this is 5%. So I read 1 and get to 5% here. If you look upward, there's a diagonal line. This and this are bounding it. So this one is 50 mm. Look at it here, 50 mm. This one is 65 mm. And we are in between the two, midway. So we say you choose the bigger of the two, which is 65 mm.
Okay.
Then to find the velocity at that point, to make sure that the velocity factor is met, you also come and find out that it's falling between these two diagonals also. Okay, and you now come down and find out that the diagonal is about 0.5. So it means that the velocity is met, the water is flowing the right velocity, and the pipe size should be 65 mm pipe, 65 diameter pipe. So all the ones that are less than 1 are all carrying 65. The one will now come to 1.75. I believe something must change in that case. So for 1.75, you go back to the charts. This is 1.5. This is 1.75. Assuming we are using the same slope of 5, is slightly below, slightly in between, slightly in between 65 and 80. So I choose the bigger of the two, which is 80. So I'll come here and put 80. This one remains 0.65. Then note 4, 2.45. I'll go to 2.45, which is almost like 2.5 against 5%. It is at exactly 80. So that one too, I will use 80. This one remain this one. $2.8 is almost close to 3. So let me just use the word. Let me just use 3. 3 against 5 per mil is somewhere between 80 and 100. I will choose 100. So here will be 100 per mil. So what you can do as an engineer is that if you list the whole flow, I think yesterday there's a chart I showed us, economic design. If you list the whole flow, you now begin to see which one fall in between. So sometimes you might not be, if there are 1,000 nodes here, you might not visit more than 50, and you design for 1,000 because some are repetitive, some will continue to be repetitive. So anyone that is below 1, below 2, below 3, and that's why in our material yesterday, I think it was in our material I showed us yesterday, where we have economic design. Somewhere in our materials, it's showing us the economic design. Sorry. I don't know which particular chapter. If I start looking for it now, it will take our time, but I know it is in one of these materials where there's an economic design, so that if the design fall between any 2 points, based on the value, you can just pick up the value and design for it. Let me hope it's here. Any question, please?
Yeah, I think, I have a question. You assume that we take a slope of 0.5%, respectively 5 promille, but I mean, it has such a, on this scale, on this nomograph, I think this unit of promille was also chosen because it makes a quite big difference if we basically what slope we take.
Yeah.
So why did you jump over the step? Why do we jumping over the step? So let's say easily of calculating the slope for each knot.
Okay. In ideal case,
it makes quite a difference, huh? In the dimensioning.
Yeah. Forgive me. I just want to. I want us to be able to finish by 6, and if we start to calculate each of those slopes, it will take us much time. But look at it, to calculate the slope, is just to take the difference between the elevation difference. For instance, let me go back to the material. If I'm to calculate the slope, for instance, let me calculate one of the slope. Stay with me. It will, I assume one slope just for ease of calculation, yeah. But in real life, you need to estimate the slope for each section. You have to. It's compulsory that so that you know you don't oversize, because the slope is a function, has a great influence on the size. So you must use the appropriate slope. Let me give you one instance, for instance. This is, which of the point can I take? Let me take point, okay. Let me take the storage, storage tank is at elevation of 310. Point 1 is at elevation of 279. So the elevation, the slope between points ST and 1 will be this minus this divided by their horizontal lengths. If we are to do this, we might miss the point. To calculate the slope is not, it shouldn't be a difficult thing. We are all engineers. So I skipped it, Robert. I just skipped it. but I explained it. I make sure I explained it very well. So the idea to use a uniform slope is just to make it easy, because the point is to show us how to read the charts and not really how to calculate slope. So the slope in this case is now 310 minus 279 divided by 120. That was 0.25. 0.25. So instead of me reading against 5, I was supposed to read the first one against 2. Against what do you call it? 0.25. So the slope for storage tank to 0.1 is going to be this minus this divided by this, and it's giving me here 0.25. So in our charts, that will translate to 2.5%. So for the first one, for the last one, which is 2.8, here, I'm supposed to stop at 2.5, which is somewhere here. And it's still giving me 100 mm. Are we together? But in some cases, the difference will be obvious. But in this case, whether you choose 2.5 or you choose 5, they are virtually the same. Okay, it's giving me 8 something. It was closer to 80, but when it's 2.5, it was in between 80 and 100. I don't know if that explains your question.
All clear. Thanks.
Some of us, one of us, he says he's muted. I can assure you it is not from our end. If you cannot hear me, I've just said what you do. You have to log out and log in again. Log out. Okay, you can't even hear what I'm saying. Because everybody here is hearing me. Okay, any other question, please? Okay. Okay, just log out and log in. I'm sorry. Okay. I'm going to do a recap. Any question? Because we have done this. Let me save it now again and try to share it with everybody.
I placed something on the chat box.
Okay. Okay. I'll see it shortly. Any other question? I can't see your question. Okay. Okay, the last material. Okay. To get the last material I shared, just go back to your Google Drive.
No, the other one you placed on my WhatsApp.
Okay, maybe after the class. That might distract me. So let me have uploaded this one again. So if you have access to the Google Drive, which I share with everybody, now this cloud thing, we need to adapt it. If you go to your Google Drive, just visit it again, you'll see that I've okay.
Okay, I will open later.
So I've shared this with us. So tomorrow, one assignment I'll have for us is that when you get back home, try to get this, try to develop this in Excel. I think I've developed one before, but I can't find it. Get this in Excel and then fill in the discharge, the slope, then the diameter. Then you can leave the rest. The rest is like what we taught yesterday. This real slope now is that after making assumption of slope, I can go back and calculate the real slope. For instance, I got something on 2.8. against 5%. And it was giving me somewhere in between here. So when I chose this, I'm supposed to go back and get the new Q and then get back the real slope. So that one is for academics. Let me just use that word. It's for academics. It's basically for academics. Any other question? Any other question?
Sorry, I have one short question. What was the minimum recommended velocity was 0.3 meter per second, and what was again the maximum?
3,
Sorry.
a factor of 10.
Thank you.
Okay. Any other question? Any other question? Okay. Okay. If no other question, I want us to open to chapter 8. Let us run down everything we have done today in chapter 8. Everything we have done now, assuming you are not writing it. Let's run down everything again. So this is chapter 8 now. Now, what we did for the branch system, the first thing we did was to calculate the maximum water demand. The maximum water demand we did was when we got 0.023. That's the water demand for the population side. Watch me. Then some areas that are industrial, we'll add 5 to it. Then for a 2 hours firefighting, if we are designed for firefighting, we calculate for 48 meter cube per hour, and they gave us this.
I can't hear.
I can't either.
Yeah, looks like he got frozen or has an issue, internet issue.
We've lost the audio.
Yep, the audio was lost for a minute. I think he's doing something else.
Hello.
We lost our lecture.
Maybe somebody can call him or something. Maybe he's not aware he's out.
Okay, let me try calling him. Okay, his line is busy, so maybe we'll wait a bit.
So now the steps we have done so far is number one, we work out our network, we determine the length and the elevation of the pipe of nodes. Then we determine the flow rates in each section. Remember, we did that. Yes. Yes, we did. The elevation at each node, we determine it by choosing either by the gross density or by number of household. We divided total areas into areas connected to a certain node. Calculate or measure areas in hectares. We didn't use this method because we are already given the layout. So we have how the houses are. Then calculate the flow rates to areas connected to each node. We did that. Then the second way is that divide pipe network into sections connected to a certain node. I explained all this thing today. Determine flow rates in section Q, beginning at the end section. We did that today. So that's the third step. The fourth step is determination of SP minimum. We did that yesterday. Our SP minimum depends on the highest floor in the area. Each floor is 20 or 2 bars. So any floor above, you add 0.5. Somebody said to send the video on the Google Drive. That's one option, but there's a free drive from YouTube. So I'll send you a YouTube link, sir. You will get a YouTube link. Musa Bameli, you get YouTube. Thank you. Yeah, you get the video.
It's yesterday. So is yesterday's on YouTube now?
No, today's on is being saved. It's being recorded.
Recording.
No, today's recording, I'm going to share it also. But what we do is we upload it on YouTube, then everybody can take it from there. I don't even understand.
Okay. So including yesterday's on.
Yesterday's on is the same thing as the one there's a 1 hour 52 minutes video I shared. It's exactly the same thing. You know, this training we've been running this training steadily. So yesterday's training has been recorded. It will also be shared.
But how about Mr. Sunday's section? Because that was your own page.
Okay, I'll share it. I'll share it. I'll share it. Yeah.
Thank you.
Don't worry. It's a done deal. In fact, before we finish, before we leave, I'll create 5 minutes before we exit. I will share it. Okay. Determination of SP minimum. There's no question. We all did it yesterday. If you are designing for an area, the highest floor becomes your reference. Okay. The highest floor becomes your reference. You don't use the lowest floor. If there are 2-story buildings in the area, then it means your service pressure will be 20 plus 5 plus 5. So you're using 30. And remember, service pressure is for you to size your tank, to know how high your tank will be. Okay. Then choice of K value. How do you choose your choice of K value? That's very simple. I wanted to go to Google and choose it. If I'm using concrete pipe, I know this value. There's a value for it. If I'm using PVC pipe, there's a value for it. So here, I will say K value. This is my Google. K value of pipe materials. I'll go to images. You see thousands of them. Look at them. There are hundreds and thousands of them. Look at it. There are K values. Okay? There are K values. Look at, there are many hundreds of them. So you can, it's an open thing. Okay? It's there on the internet. For instance, here, here, PVC pipe. PVC pipe is this is a value, but this one is in feet. Galvanized iron, concrete. Look at them. So I'll look for the one in meters. Yeah, this one is in meter. Yeah, this one is in meter. Okay, but as a rule of thumb, 0.1 is for PVC, 0.4 is for ductile or galvanized iron, then 1.0 is for concrete. From 1.0 and upward, because concrete is not the same. There are some smooth concrete and there are some rough concrete. So this is no big deal for us. Then the next thing you do, number 6, if elevated tank is fixed, then you determine your slope. And what is your slope? Your slope is simply the geodetic head of the elevated tank, of the water level at the elevated tank, minus the SP minimum, then divided by total length. This thing is just telling you the same thing we said. Elevation over length will give you slope. So this is just how to determine slope. Don't be confused by all these formulas and grammar. What this thing is just telling you is your admissible slope is the difference between the elevation over the length of that section. Engineer Sunday explained this to us before. Lower water level minus the SP minimum minus the geodetic head, which is the level of your house, the tap level. SP minimum is for you to do this. So with that, determine your slope. Chimamanda, you have a question.
Chimana is the name.
Chimana, sorry.
We have PVC, we have ductile iron, we have concrete pipe, but in practice, I've used steel pipe. Will I use ductile iron K value for?
Yeah, 0.4. Yes, sir.
Okay, thank you.
Yeah, that's a good one. Any other question? Okay, no other question. Okay. Then, after you have gotten your slope, the next thing you do is that you can now go and dimension your diameter. And your diameter will be dimensioned as a function of discharge, slope, and your roughness using the nomogram table or nomogram charts. If time will permit me, I will Google other tables and try to compare them, but we don't have to do that within our limited time. But I will encourage you, as part of checkmating what I have, the perspective I have shared with you, for you to go online, get some charts for dimensioning, and try to see whether these charts I'm using has semblance, whether they have any semblance. It's important. That's also a way of learning. And for the table that I use, the calculation sheets I say we should develop, if you go online, try to play around with Google. Maybe after the class, I'll play around with Google and I'll show you that these things are in open domain. You can download them and you can use them. You can see better ones. I know I have done it and I've seen them and they are just there. Okay. So the next thing is here. The step 7 is that you now go and dimension because you have done the previous things that you need to do. So here, the F real, you can still get the F real, which is the real slope, as a function of the diameter, the Q. You know, you have gotten the diameter now, just like what I did. This is like doing backward engineering, okay, to find the real L real now. Okay. Now, then if you now multiply the head, LU plus the length, you now get the actual losses. Then you can now work all this other one from chapter 8. From this step 8 is more like academic thing, just for you to work backwards and get the appropriate size. So if you get this and multiply by this, you work back and you get your storage tank. So all these other ones are just to give you how all these things are derived. Your lowest water level in the storage tank minus your head loss will give you the hydraulic grade line. Then your SME minimum must be greater than, this one says 30. This is German method. Remember, this is the minimum pressure in the network is 30. But here I always say, even if it's below 20, it can still go. Then the maximum is 80. And the 80 is by the highest water level in your storage tank minus the elevation of your house or the elevation of the zone. That will give you the SP minimum. And this thing means that your maximum pressure must be less than 8 bars or 80 cubic meter of water. 80 meters of water column. And your minimum pressure should be more than 30. Please, I want us to take note of this. There's always boundary conditions.
So I have a question. What does the question mark mean behind 30 and 80 meter water column?
Is it met? It's like, is it met? Is it exceeded? It's asking you, yeah, it's asking you, is it met? If it's met, if it's not exceeded, then you pressure zone. You zone them into pressures, which my colleague taught us yesterday.
Thank you.
Thank you, sir. Okay. Then, if elevation of storage tank is not fixed, if you don't know the elevation of storage tank, you simply dimension your diameter as a function of the diameter of the flow, and that is the economic design. You know, in engineering, we have what we call economic design. We have what we call economic design. Economic design is when you design based on economic consideration. I'm trying to look for where that material is. I think there's in one of our materials, there's a table where it shows the economic design, economic parameters. If you don't want to stress yourself going through all this rigor, there are some parameters you can use. It's not here. Chapter 7, let me see. Just hold on. Stay with me, please. There's a table where some economic numbers are enumerated so that once you know your discharge, you can easily determine your pipe size. But if you want to do the real thing, then I think it's in chapter 9. Sorry, I'm moving back and forth. I just want us to grab this and understand the whole thing, the way it should be. Yeah, I think it should be in this one. Okay. Yeah, look at it. You know, if you remember for our network, we got the maximum flow in our network is about 3. So here, 3 is less than 6. So I can just use the value for 6. In every design, there's always economic design. If you want to design, if you ask me the depth ratio of a beam, I will say the length over is it 25 or 23 for continuous beam. Okay, I'll just say the length over this, and I'll know that is less than 150 or no. You know, this is what engineers do. So here, if you're doing your design, if you establish this value, so all you need to be doing is to be looking at the flow. Once the flow is between 6 and 10, you choose 25. Once the flow is less than 6, you choose 100. Once the flow is between 10 and 15 liters per second, 150 mm pipe is enough. When the slope is less than 28, 200 mm pipe. Once the slope is, the flow is less than 47, 250 mm pipe, and so on and so forth. So this can also work. But it is not considering the slope and the velocity. So that's why we call it economic design. But if you have the slope values, you can do the exact design and get your exact value to the nearest parameter. Okay. Okay, any question again? So let's go back. I think we are done in 2 minutes. Chapter 8 again. Okay, so this is our network here. So the next one we'll talk about the loops. So it says go on with step 8 to 13 like before, but beginning at the end of the system, adding up the H, the mean of required elevation of tank. So this is how we do the network design. The next one here is the same thing, but in this case, if you are doing a loop system, in other words, here is looped and here is looped. So the first one we did, there was no loop here, there was no loop here, and there was no loop between 11 and 12. So the steps you take are the same, but the difference is that you have to now compute for your H. The process of computing your H is more difficult. To get your head loss is more difficult. But I know that what we do is that when you have this big pipe here, you have another pipe here, the smallest of these two, you assume it here, if you don't want to put a valve. Now I seem complex. If you introduce a valve here, it will automatically be, if you introduce a valve here between 5 and 10, introduce a valve between 2 and 3, and introduce a valve between 3 and 6, you're going to get this, which is a branch system. The branch system is easy to compute, but in cases of maintenance, it means some people will be without water. It means some people will be without water. The other disadvantage is that from some of these ends, you'll be experiencing sediment deposition unless you have a flush out valve here in all these ends. But when you loop them, the water can flow iteratively. It can flow back and forth. So, any other question? Any question before we end the class? Any question? Any question? Somebody says, hey, since I joined the Zoom training, I have not benefited or participated meaningfully. You are not eligible, or network takes time to connect. Please send me material. Okay, no problem. Okay. 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 Okay, noted. Please, if you know you've not gotten the material, please chat me after the class. I'm going to put my number now for everybody. And thank you for somebody that paid yesterday. If you know you've not made your payment, some people say they will pay today. Some people explain to me why the challenge they have. Please, this is my number. Chat me on WhatsApp. This is my WhatsApp number. Is on the chat box. Just chat me and I will send you the material. Engineer Aminchi Joshua, I don't know if you have the material, but there's a question for you on the chat box. Then somebody's using Joni. Okay, Joni says Kisele. Okay, noted. So tomorrow is weekend. Tomorrow is Saturday. I want to please plead with us. I want to plead with us. I'm going to share the YouTube link with us once again, so that you can, ahead of time, you can learn ahead of me. If you go to YouTube, what we are going to do tomorrow is already on YouTube. I will share the link here now so you can copy it. I'll also show you what you can do. If you go to YouTube, just type this topic, or you type a name I'm going to display now. This is my surname. Sorry, but soon I will make it Vasamba. I think if I put Vasamba, it might also come up. If you go to my YouTube link, you click on the name, then you go to playlists. In playlists, you go to design of water reticulation system. There are videos on Epanet. So this is not me at all. This is adverts. How to use Epanet to model a water. It is less than 1 hour. So I would like you to go through it. So this is what we're doing tomorrow. So let me share this YouTube channel with us. If you have time, I think somebody have already gone ahead to take a dig at Epanet. Okay. Let me share it with everybody in the room. Okay, so this is a YouTube channel. If I go to YouTube and I type design of water reticulation system, I think the first 3 videos should be one of our videos. In fact, the #1 video. Okay, the first 3 videos will be one of our videos. So you can look at it. Water reticulation design part 1. So this is the for day 1. This is what I want us to read. So if you now click on it, when you start playing, you go down here, click on the name, go to playlists. This is how to access people's playlists on YouTube. Then when you go to their playlist, you can now go down and okay, this person said it didn't find the materials. Okay, I'll share it again. Just, those who didn't find the material after the class, just share, chat me on WhatsApp. I'm going to share everything with you. I've earlier shared it, send it to our emails. I'm pretty sure about that, but some people might just misplace it, and I'm definitely going to share it again. So it's question time. The class is going to end in the next 2 minutes. If you have any question, you can share with me. I would like to take a video, but not necessary. Any question? Any question? I'll be ending the class shortly. So the YouTube channels have been shared, and please, if you have any question, just chat me on WhatsApp. I will respond almost immediately. I will respond almost immediately. If people have asked me questions from different places, and I've always tried to respond to them. In the essence of any other question, I'm going to end this class today. I'm going to see us tomorrow by 3. 3 will just for us to introduce the software, and that 3 hours will not be enough, but I'll try as much as possible and make sure you have a grasp of how to use the software. I'll make sure you have a grasp of it. Then when you start practicing, when you start improving, you can then learn more and be able to use it in the best of way. So on that note, I want to thank every one of us for coming. I'm going to end the class now. If you don't have any question, let me stop the recording.